So I had some requests to cover mixtures, and I think actually it's a good idea because it's a nice segue between the density estimation and then the next topic, which is clustering, which is very closely related to density estimation. Before we proceed, though, any questions about anything? Okay, also an announcement. You'll be delighted to know homework 2 is now posted. I thought you'd all be all right, mixtures. How many of you have taken the EM algorithm? Okay. Some of you are just shy. I think you have taken it. Raise your hand. Let me ask you again. How many of you have taken the EM algorithm? Raise your hand high. Okay, somehow I thought it was 100%. I'm guessing, looking around, it's 90%. Because I didn't put it in the notes because my assumption was you'd covered it before. Certainly 701 you've taken it, right? Yeah. All right, so I'll briefly mention it. Maybe we can come back to it later when we talk about some other algorithms. It's the algorithm that's most commonly used for fitting a mixture of normals. And it's not the algorithm that I want to talk about. It's other aspects of mixtures. So what is a mixture model? The most common example would be common day brush here. It's right in front of me. All right. Thank you very much. The most common mixture model would be something like this. I'll draw this in one dimension since that's obviously much easier. So here's a mixture of two Gaussians. So that's going to say this represents the Gaussian density with some mean and some standard deviation sigma 1 plus the second Gaussian with a different mean, possibly different mean than the standard deviation. And of course, we can easily generalize this to be a mixture of k Gaussians, and we can easily generalize it to be a high-dimensional mixture. It doesn't have to be just one-dimensional. And it doesn't have to be Gaussian, although mixtures of Gaussians are the most common mixtures that are used. And so let's look at the parameters here. Even in the simple case of a mixture of two Gaussians, there's quite a few parameters. There's pi, which is the probability that an observation is drawn from the first component. And then there's the mean and variance of the first component and the mean and variance of the second one. So the parameters there are pi, the 2 mu's, 2 variances. So we have 5 parameters. And the appeal of a mixture of Gaussians is that we're kind of staying within the parametric world, which seems oftentimes a bit easier than the non-parametric world. But I have a very flexible family. If I had a mixture of, instead of 2 Gaussians, say a mixture of 10 Gaussians, then it seems like I have a lot of flexibility and could do pretty much the same kind of thing I was doing with non-parametric density estimation. I could fit a pretty flexible family here and be something close to non-parametric by taking the number of components large enough. And also, when we talk about clustering, it has a very natural clustering interpretation. That these are representing one cluster and these are representing another cluster. We'll come back to that in a little while. So the appeal of the mixtures is it's sort of a parametric family, although if you let the number of components grow with n, it's starting to act more like a non-parametric family. And it's easy to understand, and it seems to have a lot of desirable flexibility. And for that reason, it's very popular, and for good reasons. It can be very successful. Now, I mentioned there's a method for fitting these things, so I didn't put that in the notes. We'll come back to it at another point. It's very popular. It's called the EM algorithm. It's one of the most popular algorithms probably in statistics and machine learning. And when we talk about it in detail later in the course, I'll tell you why it's used. But it's very easy to program, and it really just works in the following way. You could create a latent variable, let's call it z, which says, did the observation come from this mixture or this mixture? That is this component or this component. Remember, we're going to draw n observations here. And let me just say, first of all, how complicated the likelihood function is. So even with two components, this is just the density for one guy. If I want to write down the likelihood function for n observations, it's the product. And now I have to put in this thing. So it's the product of this sum. It's a product of sums, real messy. And in fact, if it was k, a mixture of k distributions, so let's actually put that in there. So that's going to look like this. I think I call these eta j in the notes. Let me stick to what I have in the notes. And then let's write it down more generally. And this could even be multivariate now, so this could be a vector, and this would be a matrix. This would be a multivariate norm. So it's a real messy likelihood. It's not easy to maximize. The trick for EM, which makes it easy, is you add, again, a latent variable which says, did it come from here or here? And roughly speaking, you're alternating between two different steps. One of them is kind of guessing the latent variable in a sense, or estimating the latent variable, and then maximizing the likelihood. And if you knew the latent variable, if you knew it came from this component or this component, the estimation is quite easy. So for those of you who haven't seen it before, we'll return to the M algorithm later in the course. For now, all you need to know is there is an algorithm that does something. Okay, when I say it does something, it's because it doesn't actually find the maximizer of the likelihood. That's one of the issues we will discuss on our list of difficulties with the mixtures of normals. So mixtures of normals are quite popular. Simple family. In principle, we can do maximum likelihood. Once we have the MLE, we have an estimate of the density. Let's say p theta. All right, that's fine. However, there's some problems, and that's why I call it the twilight zone of statistics. Mixture models, despite their simplicity, have all kinds of odd behavior. And a lot of properties of mixture models, in fact, are open problems. A lot of the basic properties of mixture models are still unknown to this day, despite how simple the things look. So let's talk about these problems. The first problem, which is on page 19, is the fact that the likelihood is unbounded. What do I mean by that? Let's go back to our mixture of two normals. Here's some data. So I have one component here, say, one component here. Let's think about what happens to the likelihood if I take mu2 to be centered at one of the observations and let the variance get smaller and smaller and smaller. Well, as I do that, the value of the likelihood here becomes infinite. It doesn't go to zero everywhere else because I've got another component. So you can check this mathematically that if I take one component, center it at an observation, let sigma go to zero, the likelihood becomes infinite. So what does that mean? If I drew a picture of the likelihood, well, that's a bit hard because it's a high-dimensional parameter space. But let's just pick one. Let's just pick one of the sigmas and imagine drawing the likelihood. What's going on is this. The likelihood goes to infinity at the boundary. It might have a nice maximum here, say, but at the boundary it's infinite. So technically the MLE is not even well defined because the MLE is supposed to be where is the likelihood maximized. Well, the likelihood is maximized actually at the boundary and the likelihood is infinite. That problem can be overcome simply by, don't let yourself get too close to the boundary. There'll often be very nice maxima in the interior of the space. So when people talk about maximum likelihood for mixtures, what they mean are maxima in the interior of the parameter space, not at the boundaries. So they're excluding these bad regions. When you actually run the EM algorithm, sometimes sigma will degenerate to zero. One of your sigmas will degenerate to zero. And the way people usually fix it is you restart the algorithm with sigma further away from zero or something like that. You have to do some sort of hack. Okay, so that's the first problem, is the unbounded likelihood. That's not deadly. It's annoying, but that doesn't mean you can't use these. All right, here's a second interesting thing. Since people do often use it for clustering, one of the,
Why the likelihood for infinity?
why is it infinity? Okay, so I was trying to give an intuition for that, but here's a good homework question, prove it. Just take one of the components, do exactly what I said. Set one of the components, set mu2 to be equal to one of the data points, and let sigma go to 0.
You know, likelihood is 1.
No, the density keeps getting higher and higher and higher, it goes to infinity. The density can be as large as possible. And you'll see when you multiply with the likelihood, it goes to infinity. Okay. So the second problem has to do with the modes. So people tend to think if I have a mixture of two Gaussians, they're going to have kind of two peaks, which would sort of correspond to two clusters. Unfortunately, it's not quite that simple. First of all, if I just take a mixture of two normals in one dimension and I give them, let's say, the same variance, one thing that can happen is when the two mixtures get close enough together, you only get one peak, even though there's two components there. That's not so bad. There's nothing wrong with having, if the two components are that close together, maybe you just want to say there's one cluster anyway. The more complicated thing is you can have two or k component mixture with many more peaks. Weird peaks start to show up. And this is not well understood. So the first paper I know about this is it's at the bottom of page 19 by Miguel, Carrera, Perpignan, and Williams. And this picture is taken from their paper. This is showing you, on the top here, a few Gaussians that overlap in a really complicated way, and it may be hard to see, but it's producing all kinds of little extra Gauss maxima. In fact, about 5/3 as many. So if there's k Gaussians, this arrangement they've chosen produces about 5/3 times k maxima. Is that the maximum? No one knows. In fact, there's a more recent paper by Beatles, Brunner, Fazy, and Rout, which does a very nice topological analysis of mixtures and normals, and they are able to produce, as the number of modes is huge compared to the number of mixtures, and they have nice plots of the number of modes versus the number of components. It's very unpredictable. You can have like 8 components and 17 modes, and there's all kinds of weird, unpredictable stuff. So if you want to know more about that, you might want to look at especially that last paper. It's pretty complex. The relationship between the number of components and number of modes is not well understood. It's very complicated. They only have precise theorems under very, very special types of mixtures. In general, it's not actually understood what the relationship is. So, again, that's not a deadly problem, but you just have to be aware of the fact that the relationship between the modes and the number of components is complicated, and we don't really know what it is. Okay, just something to be aware of. I would also consider that to be more of an annoyance than a deadly problem. So we're going to kind of classify the problems in terms of how bad they are. All right. Now we get to a more serious problem. If we want to use mixtures of normals, we might want to do some sort of inference, like confidence intervals or testing for the number of components, things like that. The problem is these normals are highly irregular, and they suffer from something called local non-identifiability. What do I mean by that? Generally speaking, a statistical model we say is identifiable if two values of the parameter correspond to two different densities. So in a normal with mean 5 and a normal with mean 7, the parameters are different, and in fact the densities are different. Right? So normals, mixtures of normals, or mixtures in general, have two different types of non-identifiability. One is just an annoyance, but one is the deadly type. Let's talk about the annoying one. So if I have, let's suppose, a mixture, how we put an example? Yeah. here's one mixture. 0.3 times the first normal, mean 0, variance 1, plus 0.7. So pi is 0.3, 1 minus pi is 0.7, and so on. Mu1 is 0. Here's a second mixture, so let's call this P. I call the parameters here psi, so P psi 1. Here's a second one. All I'm going to do is switch these two. So I'm going to get 0.7 pi to 1. Well, you can see that these are the same density, right? I just switched the two components. But technically, if I was listing out the parameters, pi, mu1, mu2, sigma 1, sigma 2, the actual values of the parameters here and here would be a different list. The position in parameter space would be different, but the densities are the same. That's called label switching. Okay? This is not a serious problem. All that really means is when you're doing the bookkeeping, when you look at the parameter space, it so happens that there might be places in the parameter space where this refers to a particular density, and there's a symmetry. There's another point here which looks like a different point in the parameter space, but it's referring to the same density. That doesn't really screw anything up. I mean, it makes your algorithms a bit harder because if there's a mode here, there might be a mode here too, and so it could increase the complexity of your algorithm and so on. But inferentially, that's not really a problem. So this is label switching. It's an annoyance for algorithms, but again, not a deadly problem. However, there is a more serious type of identifiability, lack of identifiability, which is called local non-identifiability, and this causes extreme problems. Let's look at just a mixture of two normals. Let's even set the variances to 1, just to make it simple. So the only parameters here, I've now reduced it to 3 parameters, pi, mu1, and mu2. Now, here's an interesting question. This is a mixture of two normals. But suppose I'm interested in the special case, which is obviously of great interest, which is when this collapses, when does this collapse to a single normal? And the problem here is, I can't really draw three-dimensionally, but you can see that, well, what happens to the parameter space? So remember, the parameter is three-dimensional here, pi, mu1, mu2. So picture like a three-dimensional cube for simplicity. What happens when pi is equal to 0? I get a single normal, right? In fact, when pi is equal to 0, what is the meaning of mu2? mu2 isn't even showing up anymore. Imagine computing the Fisher information for mu2 in that case. The derivative with respect to mu2, there isn't even a mu2 in there. So you can see that the meaning of the parameter isn't even clear. Similarly, when pi is equal to 1, I get a single normal again. I'm back in this. Imagine we were testing whether there was one normal or two. We're back in the null hypothesis. But it kind of refers to the same density. It's just a single normal. And again, mu1 would take any value. You could change mu1 as much as you want. It doesn't change the density. And there's another case, the diagonal. What if mu1 is equal to mu2? Then this mixture again reduces to a single density. And you can change pi as much as you want. It doesn't change the density. So what's going on is there's this whole subspace. It's actually a union of 3 subspaces, where pi is equal to 0, pi is equal to 1, and mu1 is equal to mu2, where these weird things are happening. The parameters, you can change some of the parameters, the density doesn't change, they all correspond to the same density. So it's not identifiable. We call that local non-identifiability. And this causes serious problems. If you try to work out, for example, a likelihood ratio test for 2 component normal versus a one component normal. So you can do that. There's no problem. You can compute the likelihood under the alternative, the likelihood under the null, like we did in 705, compute the likelihood ratio statistic. The problem is, what's the distribution of that quantity? It's not chi-squared anymore. What's the distribution of the maximum likelihood estimator? So people have written down, in principle, expressions for these things, but they're not usable expressions. Nobody really knows what this distribution is. So, for example, you can write down the distribution of the likelihood ratio statistic. Technically, it's the maximum of something called a Gaussian process. It's a very complicated thing, but it's not like a distribution you could actually use to do a hypothesis test. And all of the usual statistical theory, in other words, falls apart because there's just this weird behavior. The way I would almost draw it kind of schematically is there's like a boundary where along this boundary we change the parameter, but it's all the same density. The one density is going to kind of map to the same, it's kind of smudged out along this thing. And everything you learned in 705 or anywhere else about maximum likelihood or whatever, everything falls apart. And there are people still working on this to this day. So it's like an open research problem. There's this guy in Japan whose name I'm forgetting right now. He has a very interesting book about this, using algebraic geometry to try to deal with these problems. But it's still not clear whether bringing these tools from algebraic geometry into statistics, is it actually giving us usable procedures with well-defined properties? It's not clear yet.
Couldn't I just restrict my parameter space to avoid these weird regions since we know exactly where the weirdness happens?
That's an interesting idea. So, like, just carve it out?
Yeah, or just avoid it.
Okay, but suppose I want to know, I want to test, is it two-component mixture or one-component mixture? That's
pretty easy to check, though.
Unfortunately, it's not. If you know an easy way to check it, I'd want to know. There's no good test, as far as I know, because well, it depends what you mean, right? If I want to have a test with rigorous properties, like, a certain type 1 error rate or something like that, that's what I mean. So there certainly are procedures, and I'll talk about some of them, but what the properties are, nobody actually knows. They're very heuristic. There's lots of heuristics. I'm just talking about what can be made rigorous and formal. And of course, when you start talking about fitting K normals, the space of where all the stuff, weird stuff happens, gets very large and very complicated. Another type of irregularity was noticed by Chen in 1995, a paper in the Annals of Statistics. It's interesting, he found a very, very simple example which illustrates another problem with mixtures. So consider the following very simple mixture. It's a one-dimensional Gaussian. We even know the weights. It's 2/3. So there's only a single parameter here, theta. So if you try to do the stuff we did in 705, like you want to estimate theta, you get the MLE, but what do we need? We need to get the score function. How do we get the standard error? We get the standard by getting the Fisher information. You're going to discover a nasty surprise, which is that at 0, the Fisher information is 0. And if you try to take 1 over the Fisher information, which is how we get the standard error, you get it infinity. So again, it turns out all of our theory falls apart here. In fact, one of the basic properties we learned in 705 was that for parametric problems, usually the MLE minus the truth satisfies this. And even in this simple, this is one of the simplest mixtures you can come up with, that's not true. Chen showed, I believe he showed that the best rate of convergence you can get here is 1 over n to the 1/4. Although actually I seem to remember that there may be an error in the proof and maybe it's 1 over n to the 1/6. Which is saying that you can't estimate the parameter at the usual rate. You estimate it much more slowly. And if that's true in the simple mixture, it's probably even worse in the more complicated mixture. So even if you do manage to do maximum likelihood, behavior is not what we're familiar with. In other words, the parameters are quite difficult to estimate. Any questions so far? Yeah.
Wait, so in 705, it gave a bunch of conditions for
Yeah.
the MLE is what we expect. So which condition does this violate?
This violates the condition that the Fisher information has to be bigger than 0.
Oh.
Okay, let's keep going. So, here's another fun property of mixtures. So, one of the most popular uses of mixtures, as I said, is for clustering. But even for clustering, mixtures have some strange properties. So, let's suppose I thought there was 2 clusters. So I have, in the notes I used a different Greek letter here, but it's one I have trouble drawing, so I'm going to write pi here, all right? Let's ignore all these other problems. Suppose I can fit this, the distribution fits properly, and so on. Now remember, we can create a latent variable, 0 or 1, so that for each observation I can imagine I've drawn from this normal with this probability, and I've drawn from this normal with probability pi, and I can imagine a latent variable 0 or 1, which tells me did it come from the first one or the second one. And one of the nice things about mixtures is now when I do clustering, I can do soft clustering. Instead of just putting the observations into one cluster or the other, I can compute what's the probability it came from the first one or the second one. I can do that just by Bayes' theorem. So once I assume that these parameters, in fact, let's assume the parameters are known, just to make the problem easier. And I observe an x, I want to know what's the probability it came from this component. So what's the probability z is equal to 0 given x is equal to x? Well, I just do Bayes' theorem. What's the probability of x under when z is 0? That's just, I'll call this one phi 0, phi 1 for simplicity. So that's just 1 minus pi 0 of x over 1 minus pi 0 of x plus pi 1 of x. So this is a smooth function of x, and what it does is it tells you for each x, I can tell you what's the probability it came from the first one or the second one. It's basically like classification at this point. So that seems good, but a weird thing kind of happens. Depending on how the configuration of mu1, mu2, sigma 1 and sigma 2, let's suppose mu1 looks like this. Here's mu2. Let's suppose sigma 2 is smaller. Let's plot the probability of coming from the first component as a function of x. It turns out, well, not surprisingly, if you're over here, it's going to be close to 1. When you get here, it's almost certainly, there's a very good chance it came from component 2, so this probability of being from component 1 is going to go down. But the strange thing is it's going to go back up to 1. And that's because this one has thicker tails than this one. And this is just mathematically correct. It just says, if I get a big observation, I'm going to classify it into the first group. And in some sense, that's correct if we take this model very seriously. But somehow, this doesn't seem to be capturing our notion of clustering, which is, we kind of want to say this is cluster 1 and cluster 2. So whether that's a problem or not depends on how you view the model. But it certainly is a bit counterintuitive. So I would consider that one maybe a minor problem rather than a serious problem, but something to be aware of. All right, next problem. I shouldn't call them problems so much as conundrums, because I actually find all these things interesting. I mean, this is what mixture models to me are really fascinating, because They're very intuitive, simple models, and yet they have, the fact that they have these strange properties makes them really interesting. So here's another interesting problem. So remember when we did Bayesian inference in 705, one of the things we could get away with is using improper priors. So remember when we did, let's just go back to the normal. The way we got the posterior distribution was we multiplied the likelihood times the prior. And one thing we saw was that we can take the prior to be what's called improper, like take pi of theta to be 1. That's not a real prior because it integrates to infinity. And yet, most priors used in practice are improper. Why could we get away with that? The reason why we could get away with that is even though this is not a well-defined probability distribution, when we multiplied it by the likelihood, the posterior was still a well-defined distribution. And so that's a very handy, convenient thing. You can just use an improper prior distribution, multiply it by the likelihood, you still get a well-defined distribution. Mixtures, unfortunately, not true. If you use an improper prior, the posterior is improper. The posterior doesn't integrate to anything finite. Another strange property of mixtures. What that means is if you're going to do Bayesian inference for mixtures, somehow you have to be really careful about the prior, and in particular the convenience priors that people often use, like flat prior and means. You better not do it. And in fact, if you try to just throw it down and run your favorite algorithm like an MCMC, you're going to find you have problems getting it to converge. And this is the reason why. Because you're actually trying to sample from a function which is not even integrable. So, it's just yet another example of an odd kind of behavior. All right. If I haven't blown your minds too much, we'll keep going. The next problem is how do you actually estimate the parameters? So this is really interesting because we've been using mixtures for, I don't know, 100 years, and we still don't know how to estimate the parameters. I mean, I said you could do maximum likelihood, so we take likelihood function. But there's some problems. It's a multimodal likelihood. It looks maybe something like this. So we know how to maximize convex functions, or I guess, which one's that, convex? Yeah. We know how to maximize, I always get convex and concave. I guess I meant concave. Yes, we know how to maximize concave functions. But when they're multimodal, it's, we really don't know what to do. And so we don't really know how to find the MLE. In fact, I believe it's, in general, it's going to be NP hard. So what do people do in practice? Well, one thing people do is they run the EM algorithm a few times with different starting values, cross their fingers, and call that the MLE. I'm not kidding, that's the most common thing. There has been an interesting line of research, actually mainly in the CS community and the ML community, about using other types of estimators that aren't related to likelihood to try to estimate the, find the MLE using completely different techniques. There are some claims now that there are polynomial time algorithms that actually do find the MLE. But my impression so far, I could be wrong about this, but my impression is it's, let's say there's two different types of algorithms. There's the algorithms that you can actually run on your computer and get an answer. And there's the algorithms that people publish in theory papers with a proof that it's polynomial time, but that nobody could actually ever program this and use it. And I don't mean that as a pejorative, I just mean there's a different gap right between, just like in statistics, there's a gap often between the things we can prove about procedures and the ones we actually use in practice. Same with CS theory. There's often a gap between algorithms in the formal sense of the word versus something you would actually run on your laptop. And many of these algorithms that I've seen, they're very clever and very interesting, but they don't seem to be practical as far as I can tell. They either have, well, there's two types actually. There's some that are quite practical, but they make a lot of restrictive assumptions. Like, for example, that you're only dealing with well-separated mixtures or spherical mixtures or things like spherical Gaussians, things like that. Or there are these very complicated things that it's not clear you could actually code and use them. So actually finding the MLE in a practical way that's reliable with guarantees, to the best of my knowledge, that's still an open problem. So it's funny how some people are just very pragmatic and say, well, let's not worry about it. Let's just find the best estimator we can and use that. And maybe that's fine. But it would be nice if somebody could close the gap. Okay. Finally, there's the problem of how to pick k, the number of components. This is a biggie. This is really difficult. How do I know? Do I use 2? Do I use 3? Do I use 4? Do I use 20? So there's been a lot of work on this. One approach is to do hypothesis testing, but as we've seen, it's not clear how to calibrate that. We don't know the null distribution. If I'm testing, it's a mixture of 10 versus 11. I can construct a test, but how do I know when to reject? How do I know what the distribution is so I know I'm in the tail of the distribution? And again, the distributions are so complicated, we can't do that. There are various model selection criteria. We learned these in 705. So for example, you can take the log likelihood that the MLE minus, I'm trying to remember what AIC is. It's, I guess it's just, let's call it, well, I don't want to call it K, I'll call it D of K. Here I'm fitting a mixture of K normal. This is the number of parameters involved. Yep, the means and the variances, the covariances, so there's a lot more parameters than K, but it depends on K. So remember, this is AIC, which we talked about in 705. And there was the other one that's very popular, which is called BIC, which was D. So you can certainly compute these and choose K this way, choose K to maximize this. But again, unlike standard models, so in the typical parametric models we deal with, we can prove things about this. We can show that they choose good models with high probability. We understand their properties and so on. But again, with mixtures, the behavior is really unknown. There's a few papers, mainly from France, which have made some progress understanding these things, but the results are very, very complicated. And as far as I know, we don't have really precise results about what these things are actually doing. Guarantees that they're doing something good in general.
Is that because you can't find the MLE for the...
It's not, I'm ignoring now the computational problem. Even if we can find the MLE, it's figuring out what the properties of this statistic are it's very nasty. So again, I think what people do in practice is they say, okay, let's be pragmatic and we have to do something, so let's just use one of these things, and maybe we can't prove it's doing something optimal or doing something good, but we have to do something. Now, here's my view on all this. So what should you make of all this stuff? If you have a really good reason for using a mixture model, then probably this shouldn't dissuade you. I mean, if there really is some reason why you think a mixture model is the right thing to use, then by all means use it, but just be aware that there's all these difficulties. But you might want to step back and ask, do I really need a mixture model? What am I using it for? If you're using it to do density estimation, which is what some people do, just use a kernel density estimator. It's 1,000,000 times easier than a mixture model. It's simple, and we know all of its properties. So in terms of density estimation, I honestly don't see any advantage as mixtures over something simple like kernels. If you're using it to do clustering, well, we're about to talk about a lot of clustering methods, and in my opinion, there's much better methods for doing clustering than mixtures. Much easier, and again, things that we theoretically really clearly understand. So I would personally not use mixtures for that. But again, there could be other reasons why you're using a mixture. So my advice is, if you need a mixture, use it. Just be aware of the problems. But always stop and ask yourself, do I really want to be using a mixture here, or is there something else I could use? Okay, so that's the twilight zone of mixture models. Yes?
What would be one reason where you would want to use a mixture?
Well, you might be doing some biological problem where scientifically there's some reason to think that what you're dealing with is a mixture distribution. And so it makes kind of scientific sense to be using a mixture model. That would be an example.
How about like topical models like LDA or things?
Yeah, so you're right. So in certain language models, like document modeling, and you think of each document as a bag of words that comes from a mixture distribution for different topics. There's a good example where mixtures work well in practice. No one will ever understand the theory of those models, as far as I'm concerned, but who cares? That's a case where the theory doesn't matter, right? We're not trying to do scientific inference in those models. All you want is you throw in a bunch of documents. What comes out, is it useful? It's a black box. Do I get documents classified into a reasonable way? And if it does, you can reasonably argue that the theoretical difficulties aren't that important, right? So yeah, there's a case where I think mixtures have actually been very successful. And you don't need to know the detailed statistical theory of the model in a situation like that. Although I have to wonder in that case, there may be alternatives that people are overlooking that may be also useful in those cases, but I don't know enough about it to say for sure. Any other questions?
Can I ask about kernel density estimation?
Sure.
How should we understand that to be something like infinite parameters, like what functioning is?
Well, I wouldn't think about it. To me, it's just you're right. It's an object living in an infinite dimensional space, but so is the thing you're trying to estimate, the density. So to me, it's just an estimator. It happens to be a function. And we know all of its properties. We know at what rate it converges. We know how to choose the bandwidth. We know how to construct the confidence bands. So the fact that there isn't finitely many parameters doesn't really pose any problems. In fact, oddly enough, it has more parameters effectively than the mixture model, yet it's simpler. Right, we understand it has a central limit theorem. We know it's consistent and so on. So somehow, the fact that a mixture model has fewer effective parameters didn't make it any easier to understand what was going on. It's kind of interesting. All right, any other questions? All right. So let's move on to clustering then. Clustering, of course, is another unsupervised problem. And I think of unsupervised problems as being much harder than supervised problems. And there's a lot of ways to do clustering. We can't possibly cover them all. And probably you've seen most of them. So the goal here is to add a little bit of theoretical meat to some of these methods, to say, what are they doing theoretically? As opposed to just the algorithm, which you would have seen most of the algorithms in 701. So probably most of you have either used or at least aware of k-means clustering. That's probably one of the most popular. And we'll talk about k-means and what its properties are. And hierarchical clustering. The newer ones like spectral clustering, we'll talk a bit about that. I'm actually going to start with some less popular ones, but I think I'm starting with these for two reasons. One is there's a nice segue here from the density estimation work to these first few clustering methods we're going to talk about. But I also think personally, I think they're better. I think they're on firmer ground. So in particular, we're going to start with mode-based clustering. How many of you, this basically means doing a density estimate and finding the modes and basing clusters on the modes. How many of you have come across mode-based clustering before? Not too many. How many of you have heard of the mean shift algorithm? Small fraction. There's an interesting sociological thing here because people in computer vision and so on, they use this thing called mean shift clustering all the time. It's very popular there, but somehow it hasn't permeated ML and stats, even though it's actually, I think, a great algorithm. So I'm going to actually start with that. I'm going to start with these, what are called density-based methods. Density-based clustering, there's kind of two types. There's probably more than two, but two main types. One is mode-based clustering, which I'm about to describe, and then there's something called level set clustering. Then we'll move on to the more traditional ones like k-means and so on. All right, so since we've learned now how to estimate a density, let's see if we can put it to use. So mode-based clustering, or mean shift clustering, as it's sometimes called, looks like this. So I get some data. I estimate the density. Let's say I use a kernel density estimator. It doesn't have to be, but let's say it's a kernel density estimator. Let me draw one in one dimension. So what we're going to do is, first of all, we're going to locate the modes. It seems like a natural way to define clusters is basically, what's a cluster? It's a region of high density. I think one of the important things in cluster analysis is don't start with the algorithm. Start with a definition of what you mean by a cluster, then find the algorithm. So I think a lot of the algorithms are just intuitive, and then you ask, what is it actually estimating? It's kind of hard to say sometimes. So I want to start with a population quantity. If you gave me the true density, I'm going to define the clusters to be, start with the modes, and then I want to associate which parts of the sample space are close, in some sense, to the different modes. Now that raises the following question. Which things should I associate with this mode, or this mode, or this mode? So in mode-based clustering, what we typically do is we look at the density and we say, if I were to follow the density, if I were to actually follow the gradient of the density, where would it be increasing? The derivative is going up here, right? In other words, if I was an ant climbing the density, and I always climbed up, I'd start here and I'd end up here. So it's pretty clear, any path, if I draw it here, if I'm an ant and I go up in the density, I'm going to go like this. Or if I start here, I'm going to go like this. So it's pretty clear that these are all the points that would climb up to this mode. That's called the basin of attraction of that mode. And similarly, you can see if I'm in here, if I'm an ant here and I always move in the direction where the density is increasing, I'm always going to go here or always go here. So this will be our second cluster. And finally, this will be the third. We'll define it more precisely in a minute. But it's really just pick any point and imagine you always climb up the density, always sort of increasing gradient. Take the gradient ascent path. You're always going to end up at a mode. And so that uniquely assigns every point to a mode. What I said just a second ago is strictly speaking not true. I said every point will always end up at a mode. Actually, there's a technicality there. All points except for a set of measures 0. So I'm not going to worry about the set of measures 0. So that defines our clusters. Now in higher dimensions, it's a little bit trickier. Let's suppose I have a mode here, mode here, mode here, mode here. We're going to have to define things a little bit more carefully. But imagine there's a density sitting over the blackboard. And again, I could ask, if I pick a point here, imagine going up to the density and following the gradient ascent path, climbing up the density. It's going to partition the space, maybe like this. These points all have paths going to this mode, and so on. Here, 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 here. So I'm going to just define that formally for you. It's just a differential equation, but the differential equation just formalizes what I just said, which is at any point, if I start at any point here, let's call that point x, there's going to be a path, I of x, that's a path. What's a path? A path, think of it as something indexed by time. At time 0, I start here, and as time increases, it moves, and I'm calling it an integral curve or a gradient ascent path if it satisfies the following equation. If this is just the gradient of the density at that path. So all that's saying is, I'm sorry, I forgot the derivative. So all I'm saying is that path is defined by the property, you can see it more clearly here, that moving on that path, it's following the direction of the gradient. It's moving up the gradient. That's all this is. This equation is saying. Does that make sense? I hope that this is a differential equation, but it's just saying exactly what I said. At every point, I can always just move up. Imagine, in fact, if you did gradient descent. This is just saying you're following gradient descent. That's all it's saying. You're moving pi. That's the motion of pi. Is precisely the gradient of p along that path. So what that does is, at any point x, if I start here, these things I've been drawing really is I'm saying what happens as t goes to infinity. That's called the destination of the path. So the destination of x is just the limit of this path. And it can be shown, again, except for a set of measure 0, that every one of these paths always goes to a mode. And in fact, these paths are a partition. They never cross except at the modes. There's some conditions on the function that are required for everything I'm saying to be true that are quite weak. Do I have a picture of this? I didn't draw the path there. There is a picture on page 3 of a 4-mode density and what the corresponding bases of attraction look like. So if we have, let's say, M1, M2, up to, let's say, K modes, for each mode now, there's a basis of attraction, the things that would go to that mode. So I think I called that, A sub j, is simply the set of all x's such that the destination of x is mode j. And this is what mode-based or mean shift clustering is based on. Just get the modes, we find all the things that flow up to the modes. Another way to think about it is if you took 1 over the density and let water flow down, when you put a water drop on, it's going to flow to one of the modes, and that's all that you're defining. Okay? How are we doing on time? Okay. So that's the population quantities. I'm assuming here, by the way, that there's finitely many modes, but I'm not assuming we know how many there are. I'll just assume there's a finite number of modes, and that defines these things. For those of you who are familiar with this stuff, I'm also assuming this is called this function, that the density is what's called a Morse function. Some of you may have heard of that. Basically, it means that the Hessian of the density at the critical points is non-degenerate. So we're ruling out kind of weird structures. So is the definition clear? All right, now how do we actually implement this in practice? Well, that's the cool part, is there's a very simple algorithm for this. So, first of all, well, we know how to estimate the density. So I'm going to do some sort of density estimator, let's say a kernel density estimator. It's very common to use the Gaussian kernel because the Gaussian kernel has special properties when it comes to modes. For example, imagine I'm doing just say one-dimensional density estimation, and imagine I compute the density estimator and I count the number of modes, and you might wonder what happens if I change the bandwidth. If I make the bandwidth smaller, what do you think will happen to the number of modes? By increase, right? The Gaussian kernel is actually the only kernel with that property. The Gaussian kernel has the property that when you decrease the bandwidth, the number of modes can only increase. And it's necessary and sufficient that the kernel be Gaussian for that feature. So that's one of many reasons why people might want to use a Gaussian kernel for this. At any rate, we can certainly compute this, but now comes an interesting question. How do I find the modes? If I give you a density, how do I find the modes? Well, in one dimension, you can just do a grid search. But suppose it's in 10 dimensions, you're not going to do that. Well, This was the discovery in, and I think it was computer vision, was that there's a very simple algorithm to actually find the modes. This is the mean shift algorithm. So actually, it's really important to distinguish the method, which is mode clustering, and then the algorithm that's used to implement the method, which is mean shift. Sometimes people put them together, but in principle, you could use other algorithms to find the modes. You could just do some sort of gradient descent algorithm, for example. But the reason why the mean shift algorithm is popular is just because of how simple it is. So let me explain how it works. Let's go back to here. I've computed the density estimator, but it's stored in my computer somewhere. I haven't plotted it or anything. Now I want to find the modes. So what do? Well, you pick a starting point. For the moment, I'm just going to pick an arbitrary starting point, let's say little x. And now what you do is an interesting thing, is you just take a local average of all the points around x. So we take xi. I'm just averaging all the x's, but I'm using how close the x's are to this starting point x. So points that are far from the starting point are going to get downweighted by this kernel. And then we normalize it so that these weights sum up to 1. Okay, so all I'm doing is taking, if I look at this picture, imagine the data are over here. I'm just taking an average of all the x's, but I'm giving high weight to points in here, this point, and low weights to things that are farther away. And that, I do that, and I get a new x. So that defines a new point x. Now I repeat. And it turns out you can prove that this leads to one of the modes. Okay? So this, you can see how simple this iteration is, I hope. And now, but what do I use as starting points? You can pick any points as you want, but the most common choice is to use the data points themselves. But you have to keep something clear. There's a difference between the points I'm using as starting points and then following them, and the data points that appear in the algorithm. You don't, well, you may or may not want to change the x's as they move. So you should keep, am I being clear about this? If I take one of my starting points to be xi, I apply the mean shift algorithm, I'm going to move it. But when I use this formula, I use the original xi's, at least in the standard way you do mean shift. There's actually versions where you do move the x's. The main version is you should think of this point you're moving around as different from the data points, even though you happen to choose the data points as the starting points. So what's going to happen is, and I put a picture of it. Oh, well, here's a really simple case. So this is on page 4. The algorithm's in the box there. And I drew a really simple picture so you can see what's going on. This is an example where I have some data here and here. And when I run it, what happens is, so this point goes somewhere, this point goes somewhere, this point goes somewhere. So you can see these are all going to one mode, and similarly, these all go to this mode. So what you end up getting out of this thing is actually two really cool pieces of information. One is you've now found the modes. There's two modes. But not only that, to do the clustering, I have to ask for each observation which basin of attraction is it in. You get that for free. This point belongs to this mode, this point belongs to this mode, this point belongs to this mode, and so on. Get some more over here. So the nice thing about this is this really easy algorithm gives you the modes and the basins of attraction. You get all the clusters out of that. There is a tuning parameter, which we'll come back to, which is h. But, you know, h is not such a hard parameter to choose. Much easier than k and k-means, as we'll see. There's always a parameter to choose. It's just one of the annoying things of life, but at least this one we know a lot about. Right, so before I proceed, I want to make sure, is the basic algorithm clear? Any questions about the algorithm?
Why don't we use gradient?
So, why am I using this algorithm to find the modes? So one of the things that was on actually a homework last year, maybe we'll put on this year, is this, but we haven't covered gradient descent yet, but this turns out to be exactly a type of gradient descent with an adaptive step choice. So you are doing gradient descent. However, there's always a price to pay for simplicity. This algorithm is really simple. I never chose a step size or anything like that. It turns out it's actually not an efficient method. So there is a computational problem that I've glossed over. Let's suppose I have some points like this and this. Let's put a point over here. If you actually plot the paths, and it's actually kind of fun to do this, what you'll see is it doesn't, something like a pointer here doesn't quickly go to the mode. What it tends to do is it very quickly moves here, and then it tends to follow something like the first principal component actually, and then it goes really slow. So this is simple, but it's not the fastest algorithm for finding modes. And you have some options then. You could try to just do plain old gradient ascent, or there's a large literature on methods to speed up the mean shift algorithm. So it really depends on whether you can live with it being slow. And you know, what does slow mean? So I remember last year we had a visitor, Miguel, I can't pronounce his last name. It's a complicated Spanish last name. And he's one of the world experts on the mean shift algorithm. And so we were talking about this, and I said, look, I have to admit, Miguel, I always just use the plain old vanilla machine, the mean shift algorithm. It usually converges pretty fast, 10 steps, 12 steps. And he said, oh my God, 10 steps, that's forever. You know, because it really depends on your applications, right? He's an engineer and a computer scientist. He wants things to be really fast. I'm kind of used to waiting for things a little longer. And also, I'm doing things with thousands of data points. He's doing image analysis problems where he has literally millions and millions of data points. And so the difference to him between converging in 3 steps or 10 steps is huge. So if you really want efficiency and you want to be fast, you probably shouldn't use the standard mean shift algorithm. But if you're happy with something that you can let it run for 10 or 15 steps, and you don't mind waiting a millisecond or whatever it takes, I mean, really, you know, for data sets that aren't too big, then you can use the regular one. But it certainly isn't the only way to find the gradient descent path. It's just easy. Yeah.
Is the number of clusters the same as the number of the nodes?
So, there's some recent results. I think we're going to talk about that. We're going to do a theorem, talk about a theorem in a minute, that yes, under certain conditions, you can prove that the number, you might get, let's say, L modes when there's actually K modes, but you can show, as n goes to infinity, that eventually L is equal to K, and that these are close.
Well, this needs to overfit.
No, it doesn't overfit. It gets exactly the right modes. The question of overfitting here is not about the number of modes, because that's happening automatically. The data are telling you how many modes you have. The overfitting would occur if you chose an H too small.
So does that result for the real density or the smooth version?
Both. So there's a result for the smooth version and a result for the true version. Yeah. Is that what we're going to do next, perhaps?
Intuitively, what is H? When you vary H, what do you do?
Well, remember that H is controlling the smoothness of the density. So if what you're going to find, you know, if H is big, let's suppose the true density looked like this. If I chose H really big, I'm just going to get this.
So you're going to diminish
I'm going to lose some modes. On the other hand, if I take H too small, I'm going to get extra modes. Like this. I'm going to show you, though, that there's a way to choose H, which seems to work well for doing clustering. I'll come back to that a little bit later in the class, probably next class. Some people do this for lots of different H's, and they create what's called a mode tree. They just show like a tree showing the modes splitting and so on. So a kind of sensitivity analysis like that is another thing you can do. But there are ways to pick H. Any other questions? One of the nice things about this method is that it does allow you to find arbitrarily shaped clusters. So k-means, as we'll see, and you probably know, is sort of good at finding sort of spherical kind of clusters, or approximately spherical. But if you look at the ones at page 6 and page 7, the pictures didn't come out, something happened weird with the pictures. But these are, I chose these examples. This is called the crescent example and the broken ring, and I chose them because they're known to be really nasty. Trying to find these clusters is really hard. And I'm sorry, the picture quality didn't come up good, but what I'm showing you there is the data on the top left. The top right shows what happens after I run just a few steps of mean shift clustering. The bottom left, I didn't talk about it. It's something called the blurred mean shift algorithm, which is a speeded up version. The thing to notice is it's working pretty good, but it does screw up a little bit occasionally. So for example, if you can see in here, there's a guy that's just assigned to itself. So there's an extra little mode here. Now whether you consider that terrible or not, I guess depends on the application. And in fact, you might want to do post-processing. Sometimes people will take really small clusters and just throw them away or something like that. But these are really tough examples, but they're good ones to use for testing out if you think you have a good clustering algorithm. The point, though, is that the shape of the cluster can be anything. There's no assumption here that the clusters have any particular shape. All right. Good. So section 2.1, the notes is called choosing the bandwidth. So how do you choose the bandwidth to do good mode clustering? This is another example of something I think is not settled. I think there's lots of room to do more work here. But I'm going to tell you two different possibilities. So one idea is this. When we're doing this clustering, what are we doing? We're estimating the gradient field, really. Here's a mode. Here's a mode. We're trying to get these paths to the mode. These paths, as we saw from the differential equation, involve the gradient of the density. So in a sense, what we're really focusing here is not even just density estimation, but the gradient of the density as well. And as I mentioned in the last lecture, there are methods to choose the bandwidth to get accurate estimates of the gradient. So arguably, what we should be trying to aim for is trying to estimate the gradient well. And I just repeated something here that was in the last notes, which is there is a formula for cross-validation for estimating derivatives, and in particular, I put it down for the rth derivative here. Even if you just put in r equal to 1, there's a cross-validation formula for trying to find the optimal bandwidth to estimate the gradient. So you can just plug it into this formula, or this more complicated looking one down here. The formula is a bit of a mess, but it's just doing cross-validation. And that might be more appropriate than just trying to do cross-validation for the density itself. It tends to lead to slightly bigger bandwidths, which is a good thing for clustering. Overfitting in clustering is probably better than underfitting. If I have a density that looks like this, remember what happens if I take H too big? I'm kind of doing this, right? We know it's a bit biased. I didn't draw that very well. But so what? In terms of getting the clusters right, you can have a very biased estimate of the density and still get the clusters pretty much correct. So a little bit of oversmoothing doesn't hurt you in this case. Whereas if you undersmooth, you're going to get all these extra peaks and you're going to find all these extra clusters. So you might be better off oversmoothing rather than undersmoothing. Choosing the bandwidth from cross-validation for estimating the gradient does oversmooth in the sense that it tends to give you bigger bandwidths, because the gradient estimator is more variable. So that's one approach that some people use, is they use the cross-validation formula, but not the usual one. They use the one for estimating the gradient. Okay. But there's a second approach, which might be even better, but I have to explain a few other things before we get there. So I'm going to come back to method number 2 later. I guess on Monday's lecture. In fact, let's now talk about the theoretical analysis. So look at theorem 3 on page 7. This theorem tells you the properties of mode clustering. So the first thing it says is, I'll just summarize them here, that for every mode of the true density, remember there's three objects here. There's the density, there's the density estimator, and then there's this thing I keep calling a piece of h, which is the mean of this or a smooth version of this. So it's good to distinguish all three of them. And I've done that in the theorem here, is that for every mode in the density, and these statements all hold when n is large enough and h is not too large. For every mode in the true density, there exists a mode in the smooth density. It's 1 to 1, and the distance is order h squared. That's just like the bias in some sense of the density estimator. The distance between the, let's call it the estimated mode, and this guy is the second equation. And this is the rate. If you take the point of view that for clustering, you don't even need to let h go to 0, because all we really care about is the shape of the density. So if we think of h as fixed, then this is root n. But if you let h decrease, then you get this. Notice it's not d, it's d plus 2. And that's because the gradient is involved in getting the modes. And the distance between this and this is the sum of these two terms. It's like a bias variance trade-off. So actually, I'm not going to go through the proof, but I put the proof of most of these properties. I didn't put the whole proof in because it would be kind of long, but it's not very difficult. And the most interesting part is proving this. And I just went through it here. It's just Taylor series kinds of expansions. There's nothing difficult, but if you're interested, just read through this. This is only half a page long, and you'll see why it's true. The part that I left out, though, but I'll explain to you how it works, is first you need to show, how do you show around each mode that there even is a mode in the density estimator? That's not too hard to show. What you do is, if this is the mode, MJ, you put a ball, okay? And we know for large n, p hat is getting close to p, and we know the true p has a bump here. So if you think about p hat, well, first of all, p hat's a continuous bounded function. This is a compact set. It must have at least one maximizer somewhere. The only problem would be, could it be on the boundary? Otherwise, it's an interior mode, and then it's a mode. And all you do is you make an argument like this, where you split it into, like, say, 3 pieces. And it's not hard to show, because p hat's converging to p, that for every point in here, there'll always be a point here with higher density. Therefore, the maximizer can't occur here, therefore it's interior, therefore there exists a mode. So it's that kind of an argument. And once you establish the existence of one mode, you can show there can't be two, under the assumption that it's a Morse function. What is a Morse function? That the Hessian is non-degenerate. To have two modes close together, the second derivative would have to make a big blip, which can't happen. So if you didn't follow that, don't worry about it. The point is, it's not too hard to show that around every mode, there's always going to be one and only one estimated mode when n is sufficiently large with high probability. And then this establishes that they're close.
Can you just go through the 3 M's and what each of them are?
What is the 3 M's? Okay. There's the true density, has a mode, many modes, let's call the Jth one MJ. There's the density estimate, has a bunch of modes, which I was denoted M hat, that's the Jth one with bandwidth H. And then there's the mean of the density estimator, or the smooth density, also has modes. So getting this close to this, I was basically doing a triangle inequality, that this is close to this, and this is close to this.
we assuming that the number of modes are the same?
No, that follows, because we get, first of all, we can show there's one and only one mode in here, and then you can show, I didn't say it, but outside of these balls, there can't be a mode. Yeah. So it can be proof. I didn't put the whole proof in. Did I give a reference? I think I gave some references here, but I didn't put the whole proof in because it's kind of long, but it's not difficult. It all follows basically from the fact that p hats conversion to p. So we're going to talk about all the other types of clustering on next class. The nice thing about mode clustering, though, is that the population target is clear. It's clear what we're trying to estimate. Population density defines some clusters, and we're just trying to estimate those. And we can say all kinds of theoretical things about them, and there's simple algorithms for doing it. And again, if you want faster algorithms, they're not as simple as the mean shift algorithm, but there are faster ways to find the clusters. Okay, so that's mode clustering. Any questions? Any other questions? All right, so I guess this is Wednesday, right? I lost track of the day of the week. So on Monday, we'll finish up the clustering. We're going to talk about all the other different clustering methods. And then Brian will take over and we'll start talking about non-parametric regression and non-parametric classification.